Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you today. As you step into my virtual math classroom, I got something to talk to you about. Today, I'm going to be actually recording two videos in a back-to-back format. Today, I'm going to be talking about solving linear systems of equations like I have in the past, and I've taught you three different methods. But today, I'm really going to break down the three different methods in a pros and cons format. When should you choose one if you're given the option to, and why? And why might you not choose some, right? With pros come cons as well. It's a pretty detailed breakdown. I want to kind of give you the head-to-head right now, graphing versus substitution versus elimination. Let's go ahead here, and I'm going to give you, I'll show you what all the big pros and cons lists look like at first, and then we're going to go one at a time, method by method, pro by pro, or what, bullet point by bullet point in the pros and in the cons, and just going on forevermore. So let's go and take a look at this here. The graphing list, nice and big right there, pros and cons, and I tried to really even it out, and just so you know, having more or less pros doesn't necessarily make one better or worse. All of these really bear down a lot more, that some weigh heavier than others. Some are a lot less insignificant. These are all my opinion, by the way. Well, I take that back. These are all what I decided to stress the most when it came to it. Substitution, pros and cons. And like I said, this is a smaller list that doesn't mean that the cons aren't more substantial. And then elimination, pros and cons. And I'll let you know right now that my most preferred method is the elimination method. And I think most people tend to agree on that. When they learn it, they realize that there's a lot less hectic structure to them. But of course, there are cons to it, and there are times that elimination should not be used, or it is a lot slower to use, or what have you. So I do want to break this thing down. I'm going to start with graphing, then I'll go to substitution, and I'll go to elimination. I want to read them one bit at a time here, and I'll give you examples along the way. Now, I'll let you know when I make this video, and a follow-up video where I do scattered practice problems on saying which ones I choose as viable options and why. I want to let you know right now that as I go through these examples, I won't do them all fully, number one. And number two, I'm not going to explain what I'm doing in the process all fully. I'm using the example to support what I'm talking about for that particular pro and con bullet point, and that's it. That being said, when you're watching this video, I'm assuming you've seen these methods before and you've been taught them, whether it's from me, your teacher, a book, the past, what have you. So I'm assuming you've seen them. I'm giving you strategical opportunities as to why to choose one versus the other. That's my goal in this video and the one following. Alright, so without further ado, I'm going to go ahead and get started here, and let's take a look at the graphing one. I have 4 bullet points plus a couple sub-bullet points right here. Let's just go one at a time. And first I'm going to start with the pro here. Pro number 1, you can see your solution set as it naturally exists as the ordered pairs where the graph intersects, if at all. It gives you a true idea of what your solution really means. Alright, what the heck do I mean when I say that? Look at this example right here. Now, I'm not giving you the equations to the system, but I'm giving you the lines where they intersect. If I graph 2 lines, this is where they intersect, at 3, 1. And that 3, 1 is something that I want to use and say, I can make sense of what the heck my solution is telling me right there. It's telling me that's where those 2 lines intersect. Anytime you solve a system using substitution or elimination as well, you may think that as well. But sometimes people forget to write it as an ordered pair. And this is a nice, decent reminder that it's an actual intersection location. Furthermore, recall that an infinite solution set would show both lines right on top of one another, and a no solution set would show parallel lines. So I know when I have no solution, I know what it means. The lines are parallel. Infinite solution, I know what it means. They're the same line. And I don't necessarily need to have the equations tell me that to make that happen, or for me to solve that system and kind of make that happen either. So that's kind of the big point I want to talk about for that pro there, that the graph gives you a clear indicator of what it is that you just got out of your solutions, if any of them. Second thing, easier to work with when equations are written in slope-intercept form. In that graphing is, and I'm not saying it's easier than other ones. I'm just saying that graphing, if you want to graph, it's easier to do it when they're written in slope-intercept form because I can just graph with them. Even when the slopes are fractions, because graphing is all about a rise over run. So if I just go ahead and graph these two while I'm kind of talking to you, up 1 over 2, etc., I can graph this one pretty simply because slope-intercept form y equals mx plus b is that notion of those numbers are something that are on this graph, and I clearly know what they are and what they mean and what they do. Okay, so that's kind of what I mean when I'm talking about this one here. So I'm graphing the first one, blah, blah, blah. It also has quick solving abilities written in standard form. I'm not going to graph a standard one form for you right now. I'm just going to do this one. But in standard form, keep in mind that you are, I'm multitasking pretty well. Keep in mind that you are, well, now I'm not. You can find the intercepts very simply. Set x equal to 0 or set y equal to 0 when you're doing it to solve for one or the other intercepts. The only problem with those ones are when the intercepts are not integers and they're fractions of some sort, right? It doesn't really work out to be the best in that case. Anyway, as I was talking through that, you can see that I found this ordered pair right here. It looks like it's 4, 3, and that's through graphing these two that were in slope-intercept form. Notice if I did solve through elimination or substitution with fractions, I'd have to deal with those fractions in some set. And here, I want the fractions in order to solve this one. So there it is. Third one, in real-life contexts, the graph can often tell a story about the nature of the equations, like starting points and rates, and can be useful when analyzing the situation on a deeper level. Many word problems are also primed for modeling their equations in a graphable form. So what I mean by that is, let's say there was a word problem set up for this graph. I took this one off Google. Word problem that described the set, and I can tell you what it will mean. Excuse me. When you create equations for that word problem, or when they make a model for it, a lot of them are already in standard form or slope-intercept form, and those are two graphing forms for us already that are good. I'm not giving you equations for this one because, like I said, this is just off Google Images. But what it looks like here is whether you want to have a movie membership like at AMC or Cinemark or Regal or something like that. You can pay a total maybe monthly price, and then you pay like a lot, or yearly price maybe, and you pay a lot less for the movies going forward. It's probably a yearly price looking at the number of movies. And if you don't pay an annual membership price there, you're going to pay a lot more for your movies. But what this graph really allows me to see and analyze and talk about here is that with this context, I can see that this point of intersection is telling me at what number of movies, what's this going up by 5s? 30. At what number of movies would I be paying essentially the same price if I'm a member or non-member? It's 100 and something. I don't know what, but it's at that spot there, probably 105. What this also helps me see and analyze on a deeper level is, as I go further beyond watching that many movies, how the prices compare at any set. Like at 50 movies, I can already see and compare these two price points. Being a member, I'm going to benefit a lot more if I see 50 movies a year, which is about a movie a week. And also, if I see a lot less, if I see about 10 movies a year, it shows my prices here versus one versus the other, and that's a substantial difference. I get a nice breakdown of that. Plus starting points, like I said. I'm probably paying about $45 here just to be an annual member for that theater, whereas not paying anything, obviously, and just show up when I show up. So it's nice analysis in word problems. I really like that idea to it. And the last one I want to talk about for a pro here is the viable method to solve past linear systems. Now, I want to let you know right now, this has to do with linear systems right here. But just going into the future, we are not going to limit ourselves to linear systems in scope. You might not know how to graph these two right here, especially if you're an Algebra 1 person, because I already know what the solution set looks like. I'm going to graph the quadratic for you. Quadratic problems, hang on a second, did I see that wrong? No, I got it right. Quadratic problems are parabolas, or polynomials have parabolas, U-shaped guys right here. So that thing goes like that, and then this other one right here is a linear, as you know, down 2 over 1. And I can plot those points and draw the line. When you graph these, you can see their points of intersection, and you can always graph these using a table, So when you graph using a table, just keep in mind that you can just plot those points and figure out where they go through after. And these happen to intersect together at a couple points here. Only 2 spots specifically. I think it's supposed to be this guy right here and this guy right here. So graphing that really allows me to see clearly what happened with the points of intersection. And here's the thing, there's more than one solution to this time. That's another thing that a graph can reveal that you might disregard when you're solving using some other method. This had the solutions here, 1, 3, and then 3, -1. But again, this video is going to be designed more for the linear stuff. I'm just letting you know that when you get past linear and you're looking at some other systems here, substitution is decent at times. Elimination falls apart. Okay, it does depending on the problem, but elimination does fall apart there. All right, there are cons to graphing, and what the heck are these cons? Let's go ahead and take a look at some of these here. First one, not easy to determine the solution if the lines do not intersect on a coordinate pair of integers only. Sometimes this is darn near impossible. What I mean by that is this. The last few graphs that we've seen, they intersected at like 3, 1 and 1, 4 and things like that. What if they intersect halfway through? What if you assume they intersect halfway through, but they don't really, but you thought they did because it was something in between? You know, that's something that you really have to be careful of, because you might just not know. And even if you think you might know, you got to get it exact, you know? Sometimes I do know when it is exactly halfway, and I can be better off with that. But when you solve using substitution or elimination, you're a lot better off actually solving, because you're actually calculating things when you do it that way. Whereas here, when I graph these two, watch this one. At 4x minus 7, I'll go up 4 over 1, up 4 over 1. And you can see what's going to happen here. The last ones that I graphed on, they hit at a dot. You know, I landed on the dot together with with my two lines. This time, they're going to land on something that's an in-between. And, you know, I don't know, and you don't know right now at this juncture what that actual point is right now. Is that 1.5 and negative 0.5? Is that, you know, I'll let you know. We're going to solve this one later using substitution and elimination, and we'll know for sure. But I don't know what that thing is, because it's not right on an integer spot. And that's one of the ones that, well, I don't want to solve that one by graphing. And here's the thing. I wouldn't have known it from the beginning that that was going to happen. So I might try and graph it and go, uh-oh, now I got to try another one. So sometimes it's like a false start. Okay. Graphs must be drawn to scale and with grid lines to properly identify intersecting points, I think I was supposed to say. And this isn't necessarily true, but I'll let you know with the history of my students that I've had. Their graphs, you know, if you have to create your own graph on binder paper, say, and this is, in my day, this is what I had to do. Every single graph I made, I had to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and, you know, just do this over and over to create my graphs. I didn't have graph paper. I'm not saying that I was too old to, that it was too long ago that they didn't make graph paper. Or maybe it was. I have no idea. I was in high school from 02 to 06. But, you know, I'm creating my own scale. It's decent. And the thing is, I know what I'm counting in my head when I go somewhere. So, for example, for this one right here, y-intercept of 6, I know that when I go down 8, look, I don't have to count personally myself. I know that when I go down 8, I'm going to be down at -2. And when I go over to 5, I'm going to be at that 5 there. So I'm going to be at 5, -2. I know that in my own head when I'm doing that problem. But some people are going to have a different looking scale, have it very sloppy. They count their 8 a little differently, and they move over and their point's up there. You know, it's just going to be in weird different spots here. My scale's not perfect. So if mine don't go right on perfect dots with each other, this is going to be a problem. But I hope the way that I built this problem, it will. So let's go ahead and connect that first. But you know what I mean? Once you construct these things, and here's the other part. If you don't have the graph things, that means you have to construct this for yourself. That takes up time in itself. So that's up to you whether or not you want to spend the time to make that happen, connect those dots, and then do it when you could have served a lot less time just solving it. That being said, these had fractions. You could get by them pretty fast, but just keep that in mind. Now going up 1 and over 5 looks like I'm going to hit right there. So I get my spot that I kind of wanted. So you can see that it's not impossible. When I said darn near impossible, you know, I'm really, sorry, darn near impossible was the previous one. But when I'm talking about this thing being kind of must be, that's not necessarily true. You know, I do know that this landed here at, let me do a different color, at 5, -2 for both of these guys here. But notice what I had to do to make it happen. I kind of made some math happen as well. I had to do 6 minus 8 to know that was at -2. So you have to still make a lot happen for yourself to ensure that you hit a spot. And if it didn't hit on one of these spots together, now you're way out of luck. You might as well go to another method. All right. If the points intersect far away from your graphing window range, you're unlikely to be able to reach its point of intersection with precision. So look at these two equations right here, 10x minus 20 and 3x plus 57. If I have a window range that's centered around my origin, and these increments go up by 1, I can't even fit my y-intercepts on this thing. And I know what you're thinking. We can change the scale of this. And of course we can. I can change these to go, if this goes to 57, I can change these to go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, etc. That way I can go ahead and get these points. But the problem still now comes within that being precise. Precision. Precision is going to be important for this thing. And what I'm stating with that is with 10x minus 20, this one is fine for me to do. Because as I go, I don't know if I want to go over by 1. See, this is the part I'm not sure about. If I start at negative 20 here, I can go up 10. Let's just say up 10 over 1. See, I go up 10 over 1. 1, 2, 3, 4, 5. 5, 6, 7, 8, 9, 10. Up 10 over 1, up 10 over 1, etc. I can plot those points great. Now, if this were a true scale, maybe I'd go right by tens. But then the 3 is kind of a problem, because how do I go up 3 on something that's scaled by tens? And how do I start at 57 right here, hit 60 and hit that spot? This is going to be a little mundane, and it doesn't work in a way. I'm clearly not doing this right. So you can tell, this is way out of my window range. Even if I have to zoom out to make it happen, it might not let me be precise enough. It depends on what your graph is and how it's set. This one will not let me do that. Solving by substitution on this is going to be cake. I can do that in 2 steps and I'll be done. Maybe 3. But that's all you got to do with that. Not all equations are written. This is troublesome for whichever one you do, by the way. Not all equations are written in slope-intercept or standard form to begin with. Remember, those are the 2 forms that are set up for graphing. Those are the ones that we say, that's how we graph out of by hand without a table. And these ones are not set up for that. If the y-intercept or x-intercept is a fraction, this can also be difficult to work with. So I bet if I got y by itself on these, I bet it's a nice clean y equals mx plus b, where the b is an integer, not a fraction. But you can see right now, this isn't fun for anybody involved for any kind of problem. I don't even know why I threw that one out there. But let's say you had this. Y equals 2x plus 4/5. Starting with a y-intercept at 4/5 and having to go up 2 over 1 and up 2 over 1, and you're not hitting your crosshair points and you're on a fraction portion, is not a great ordeal for that kind of problem. Again, fractions are troublesome for no matter what you do, but at least I can find ways around it when I use substitution. I just multiply everything here by 5. So fraction intercepts are trouble. Not being in slope-intercept form or standard form can be trouble as well. I think technically this one's in standard form, but no integers. That's bad. Okay, and last one here, and this is kind of a toss-up based on how you're talking about it here. In word problems where variables are not denoted as x and y, or they're not in function notation, the graphing axes now require precious labeling, meaning now you got to know which one's going to represent what. In this word problem, I have letters T and H. Which one's X, which one's Y? You'd create it for yourself, but I can't write my answer as an ordered pair because that means nothing to me now. It bears little or insignificant importance from the student's viewpoint when you see a point of intersection on some things like this. Now, we just saw one where it was about number of movies and prices paid, but these are not comparing something to a single item. I'm not sure how I'm saying this. This is for tacos and hot dogs. Those are my 2 different units here. Tacos can be X and hot dogs can be Y, sure. But going up on hot dogs and right on tacos and seeing those as increases and where they intersect, I don't know what this graph's all about, but where they intersect here, and it's not telling me enough of a story on this graph. I'm not giving myself the information that I need that I could do when solving. And you know what else I didn't list as a con here, and I really wanted to, and this word problem helps me talk about it? Decimals. Decimals are not fractions, and decimals and fractions, which are good for slope, decimals are not. Fractions all about rise over run, and I'd either have to play conversion or something like that. So decimals are no good for me, whereas fractions could be. So with graphing in that form here, again, these can just be a little problematic. They're not as fun with this. They're a lot better when you just have basic, bare bones, slope-intercept form, make it happen there. All right. Anyway, so that's going to be it for the graphing stuff. Those are the pros and cons there. I'm going to do some later examples for you at some point and show you which ones are good for graphing when I do the later 12 problems in a different video. Okay, I'm going to move on here to substitution method, and let's take a look at what this whole thing looks like in a big nutshell. I want to just give this fresh reminder here once again that just because there's a shorter cons list, that doesn't mean that these cons aren't as heavily weighed. In fact, one of them is most heavily weighed, and I want to talk really heavily about it. Now, substitution also, if you think about it, substitution is a lot like elimination in that you are just looking at the equations, not the graphs. So you're manipulating those in order to solve. So these kind of come hand in hand. There are some bullet points that will be the same for both of them. I just want you to remember that, number one. Number two, I forgot what I was going to say about number two suddenly. I don't know. Substitution is also kind of like graphing in that slope-intercept form is not a bad one. And I think that's what I want to talk about to begin with here. Okay, so here's the pros list. Let's talk about this one first. I'm going to first start with the first pro is it's best used when one of two variables is isolated in at least one of the equations. If I have an x equals or a y equals in my system somewhere, that's really good when it comes to solving, because all I got to do when I substitute is plug that thing in. Let's look at this example right here. Y equals 8x minus 5. 8x minus 5 takes place of that y. And I just sub it right in because this is isolated. That's perfect. If both equations have the same variable isolated, if I had a y equals and a y equals, substitution now becomes the cinchiest method. Cinchiest is actually a word. There's me with my big word. Saying it's a cinch becomes the cinchiest method. It's the simplest. I should have said the word simplest. Simplest method to do. And if y is isolated, you're now likely set up in slope-intercept form, making it also graphable. So you could double check. If I have y equals this and y equals that, like this one, this is graphable for me then and there. I'm in slope-intercept form. I'm good if y is by itself. So isolating y is not a bad setup if you're able to do it. Next pro, once one variable is solved for, the second variable can almost always be solved easily using the isolated equation. What I want to remind you of is that your goal when you play substitution is to isolate an equation to begin with. So let's say I chose to isolate this x right here by adding y to both sides. I get x equals y plus 4. Obviously, I do my substitution, plug that in, and let's say I solved for y, and I know for this one, y is going to be negative 3. So let's say you get y equals negative 3. Awesome. What I can do now is plug it right back into my isolated equation where it says x equals. This is fast for me to do. Negative 3 plus 4 is 1. Boom, I'm done. X equals 1. I'm done with that problem. I don't have to plug it into one of these and move things over and stuff. So since I took the time to isolate one of my variables there, it's now ready to plug in the solution of my other variable and solve it. Whereas in elimination, you don't have that luxury. Substituting is a method that students are very familiar working with from previous math practices. One of the math practices, going back to that last problem I just did, well, here, let's talk about this one. Let's say x was 2. I just plug it in. You're used to the idea of substitution, using parentheses and having it take place of something. That's a practice you're good with. The other practice, of course, is the distribution portion. Let me actually just substitute. Let's say I substitute negative 3x plus 4 in for y here. Okay. The distribution method right here is something that you've also practiced going into this kind of unit. Distribute the negative 2 here. You get negative 8x plus 6x minus 8 equals negative 16. And then you go from there. Combining like terms, all this other jazz. It's stuff that you've done before. You've done substitution. You've done distribution. You've done combining like terms. They are things that don't go beyond something you need to learn more of to make happen. Elimination is a brand new process. Substitution is a method that you've used that can be used for solving systems. Unlike graphing, it can always be used with larger numbers and can find precise non-integer solutions. Remember these two equations right here? Let's go ahead and solve it using substitution. If y equals 10x minus 20, 10x minus 20 can take place of that y, and I have 10x minus 20 equals 3x plus 57. Okay? If I subtract 3x from both sides and add 20 to both sides, and then divide 7 from both sides, I get x equals 11. Now keep in mind, I'm not done, and that's going to talk about probably one of the cons later. You got to remember, this is an ordered pair. We need to find out the point where they intersect. So I go back to one of the awesome pros with this is substitute this back into the isolated, there are two isolated equations. Substitute this into an isolated equation. Let's use the top one. Y equals 10 times 11 minus 20. 110 minus 20 is 90. So I get my final order pair 11, 90. That is where those two ones intersect. Now that's hard to graph given a certain window range, and you saw that. This one was pretty fast to make happen here through substitution. very basic processes occurred. Obviously, I gave myself a nice problem as well to make it happen, but that's the point. I'm defending when this is very useful or when other ones are not. And that's the thing where you gotta weigh them. You know, you're on a scale where you're balancing not just two things. If I had a third arm, I'd show you, but here's graphing, substitution, and elimination. And sometimes there's a tie, and you're just like, I'll just go for my favorite. But then there are other times where some really are better than others. Last thing here, it's a viable method to solve past linear systems. I talked about this with graphing, of course. With substitution, it would be the same kind of thing. I'd have this thing take place of this as well, and I could solve this quadratic equation here. If you're in Algebra 1, you might not yet be at quadratic equations, but here when I'm solving this one, and I know you might not know anything about what I'm doing, that's okay. I can solve this one through factoring, and I forget how to factor suddenly. X minus 1, x minus 3. X equals 3 and 1. So I got two solutions for x through the substitution method, and then I plug them back into an equation to solve for my two y's. When I plug in when I plug in 3 for x, I'm going to get -1. And then when I plug in 1 for x, I get 3. So we get the solutions that are 3, -1 and 1, 3. And hopefully those are the two solutions that I got when graphing. Let's look at that. 3, -1 and 1, 3. Where are they? Where's my parabola? There it is. 3, -1 and 1, 3. So again, it's possible to do through substitution there. And I said viable for both graphing and substitution, not as viable for elimination. That being said, this one is not bad, but it's still something that you just got to be careful with. All right, so those are the positives there for substitution. I'm going to go ahead and go on to the negatives here. And the first one's the big one. I'm going to just jump into that right now. It's a smaller list, but this first one is huge for most people, especially myself. This is the one that turns me away from substitution to start with. Sometimes isolating variables leads to inevitable fractions that must be used while substituting. That doesn't mean you have to use fractions the entirety of the problem. Sometimes you can mitigate it or whatever. Sometimes you just deal with them and just use them as is. But sometimes there's nothing that can be done when it comes to substitution to start with here. There are some things, but then once you hit that stage, you might as well use elimination. But let's look at a problem like this one here. When I'm trying to isolate one of these variables, remember you have to divide by the coefficients. If I divide by 5 here, problem. If I divide by 6 here, that's a problem. Divide by 3 here, that's a problem. Divide by 2 here, that's a problem. So no matter what I do, and you can make your decision, choice which one you isolate. I'll isolate this y here, for example, subtract 5x. No matter what I do, I'm going to be stuck with fractions. This is my most preferred what I'm going to do right now, because when I divide everything by -6, I'm only going to have a single fraction, and everything's going to be positive. But I do have to now use this, substitute this expression in for y into this equation. And again, I'm assuming you've seen all this stuff. So when you ask, how are you doing this stuff so fast? I'm divided by -6 on both sides of this thing, everything like that. So again, I'm assuming you know how to do some of the stuff. I'm giving you the lowdown on why this kind of becomes cumbersome. So you now have to deal with a fraction when I'm playing with this thing. And you can tell that's the turnoff for it. Whereas there's a quick way, people who know how to do elimination can see it. There's a quick way that I can solve this through elimination right now that'll get me taken care of. And this was the best way to me to getting this thing down to isolating something. All positives, one fraction, but it's still that fraction. And that's huge. That's huge. This is a big con right here. This is a big detractory statement of substitution. There are problems that work against it when you want to isolate a variable. Furthermore, you got to isolate the variable. There's that. All right, next one. Substituting leads to parentheses, thus distribution, thus combining like terms. Basically, multiple steps are still to be had. Sometimes it can get large and messy. So let's say that I take this one right here, once again through substitution. What are the steps? I got to first substitute. Then I have to distribute. Then I have to combine like terms. Then I have to move the thing over. And then I divide. And, for myself, well, you can't see that. For myself, I'm fine with it. But, once again, if there was a faster way, maybe I seek it. I'd argue this is going to be faster than graphing. I'll let you know right now. Graphing, for me, is still the slowest one. But depending on what you want to do with it, it's going to be important. And I'm not done with the problem, by the way. I still have to plug it into that and get the y value. I think it's 0. I think y equals 0 there. But the point is, it gets messy. A lot of steps. A lot of people aren't as fast doing this and making it happen. If you go through elimination, 1 manipulation, 1 cancellation, 1 division, you save yourself like 3 steps. So it just depends on the problem there. So it can get messy all depending, especially with that fraction one you saw. All right, unless applied in real life context, the solution set might not have a practical application for the student. That means, unless you're solving that hamburger hot dog problem and you get, this is how many hamburgers and tacos, this is how many hamburgers were sold, this is how many tacos were sold. This -5, -4 might not have much relevance to you. You might understand this as a point of intersection. You might, and that's good, you should. You write it as a point of intersection, you might understand it, but you probably don't know what these graphs look like. Remember, I talked about interpreting that movies one. We know what those slopes are kind of telling us in the future and in the past when it comes to how many movies you're going to be seeing. Here, if these were equations for movies, I'm not really getting much out of this. I can't see much out of this to make it happen, or that, obviously, they're not going to connect at negatives for movies. This has no real relevance to me. It bears no importance or significance to me. It's not a tangible thing. I can't see its graph and make big sense of what's happening. And furthermore, you look at a problem like this. Did you know off the bat that these two equations lead to no solution? That these two lines are parallel? I sure didn't. I'd have to know they have the same slope to do that. And to do that, I have to rewrite this into y equals mx plus b form. But if I'm solving using substitution, I'm likely not doing that with this problem. I'm likely taking this, and then I'm substituting it in for y, and now I'm doing my cumbersome distribute and all that kind of stuff here to make it happen, only to find out I get a 0 equals 7 scenario, or whatever the answer is here. I'm doing all these steps, and when I could have just graphed them to find something else and figure out their parallel, or put this in slope-intercept form to do the same thing, figure out they both have a slope of 4, then I can immediately then say no solution. So going to substitution method immediately might not give me that tangible outcome. And furthermore, when I get something that says, what would this say? It would say 2 equals 7. Once I get something that, 4 equals 7. Once I get something that says 4 equals 7 here, I know what that means, but I know my students don't. They know it means no solution, but they might not know what it means when you compare the heights of the two graphs. Okay, so and what it does mean is one of them is 3 above the other always, because 7 is 3 more than 4. So anyway, that's just one of those bits there, making sure you understand it. And finally, if the first variable solved for is a fraction, it must be used to solve for the other variable. So what I mean by that is, when I'm going to place substitution on this one and solve for x, negative x plus 1 equals 4x minus 7, when I solve for x here, 5x equals 8, x equals 8 fifths, now I have to use this 8 fifths in to solve for y. So I can substitute 8 fifths either into this one, I'd prefer not to, or this one up here, and I'm going to have y equals negative 8 fifths plus 1, which means now I have to get a common denominator and do all that. I think we get negative 3 fifths when all is said and done, but you have to work that common denominator out now. The fraction is essentially an inevitable go-to unless you go to isolate another variable. And I guess isolating this x isn't dreadful, but that's not your general go-to. You want to go and substitute in something else and make it work. So in this case here, you got to work then with that fraction and make it happen. There is a way to avoid that in elimination, and that's by eliminating the other variable. I'm going to show you that next. And that's actually the last one we're going to. So last one here is elimination. Let's go ahead and take a look at the big bullet point list here. This one's going to look a lot bigger. Pros and cons. There are good pros to elimination, obviously. There are some cons. I might be a little ticky-tacky on some of them because I'm going to tell you right now I do like elimination a lot, but there are times that I'm not going to use it, and there are times when I'm not going to use it because I'm going to use something else, and there are times when I'm not going to use it because I just do not want to use in that scenario. It is not the ideal one to go to. So I'm going to start by talking about the pros here. List of 5 right here, and you can see that this one I think it's just this one right here, is the same as substitution. So I'm not going to talk largely about that one. But the first one here, first pro, this is best used when equations are already in standard form because what you have are vertically aligned terms. You know that the x's are together, you know that the y's are together, you know that the equals are together, and the constants are together. So if we look at this example right here, these are both in standard form, and the x's are aligned, the y's are aligned, the equals pretty much are aligned here. So you know when we use elimination method, we kind of add down the list, right? We just go right straight down the slot here, and we say, okay, these two guys cancel because they're right on top of each other, and then I get this 2y equals -2, stuff like that. I can get there, boom, right there. If both equations contain additive inverse coefficients for the same variable, elimination now becomes the Cinchius method. That's what I just did here. -7 and 7 are additive inverses. Add, eliminate, done. Don't try and do anything else to isolate a variable or something or graph this. You are set. This is very, very well worked out. And many word problems are also primed for modeling their equations in standard form. I've talked about word problems working out in slope-intercept form. You create a lot of things with rates and stuff, slope-intercept form. A lot of them are in standard form too. You saw the the hamburger and taco scenario. I keep saying hot dog. You saw the hamburger taco scenario where it's this plus this equals that, this plus this equals that. A lot of them are ready for that, so be ready for elimination on a lot of word problems there. Next one, fractions are inherently always avoided in elimination work, even if it is at the cost, this should say at the cost, not as the cost, even if it is at the cost of using larger numbers. So in this scenario right here, I can completely avoid, and you can tell right here, if I want to isolate one of these variables to solve for x or y, fractions. We already know that's the big hiccup in solving using substitution. I would have to deal with fractions. Elimination, I don't have to. I can avoid it by saying, what if I multiply this top equation by 3? Suddenly I have 24x minus 9y equals -48. These guys, ignore this now. Now I have 9y negative 9y. Let's eliminate. I've avoided the need for any fractions in getting x by itself in working to solve for it. -34. So, I'm already done with not the problem, but with solving for x, and now I can use that to solve for my y in some way. Same with if I wanted to eliminate on the other side. It's just as clean and simple as doing that. These numbers would get a lot bigger though, and I'll talk about that one later when I have to double up working multiplying by 2, both equations and manipulating them. So although we normally only eliminate once to solve the first variable, it can be used to solve both variables. This is helpful if the first variable you solve for is a fraction and you don't want to use it to solve for the other. So let's say this answer was a fraction, because this is going back to substitution one. Problem with solving for one that's a fraction is you got to kind of use that fraction to answer it. So let's say I did want to, I didn't realize that bullet point was there, now I do. Let's say I did have a fraction here, and I didn't want to have to plug it in to solve for y. So instead I say, okay, well then let's just go ahead and eliminate x this time and solve for y. So let's say I say, well, let's multiply the top here by 7 and the bottom here by 8. This is where the bigger numbers come into play. Once again, that's the trade-off. That's the trade-off. I can at least now eliminate -112. I can at least now eliminate my x's this way and avoid fractions completely, and people will go to the lengths to make that happen. I'll be honest, I don't think I would have for this particular problem. Is that really 112? I guess it is. Doesn't matter what this is. This is going to be 0, so y equals 0. I know this already. But anyway, so the point is that I can eliminate the other one as well and avoid the fraction part because I can play elimination on the second one too. Avoid fractions completely. That's the good go-to. Next one. Once a variable is eliminated, the equation is clean and there's only one more step in solving equations. This is assuming standard form or something where the x's are on one side, the constants are on the other, things like that. So again, if I add straight down this list here, boom. Clearly this was one step here. I'm just making it quick. But 10y equals -10. I have one more step to go here. You saw in the substitution steps, one of the cons was I have to plug it in. Big long list. Distribute. Combine like terms. Then move this thing over. A lot more steps there. This saves a lot of them. That when you eliminate, you're always one step away. And that's that nice key thing. Again, you might have to do more, like in this problem, to get to there. But once I get there, I'm just that one step away. Okay. And, okay, two more. So unlike graphing, it can always be used with larger numbers to find precise non-integer solutions. Bet you're wondering how we would solve this one using elimination. You kind of have options. If you want to move these x terms over in standard form to make it work to start, that's fine. I'll just leave them here for now. Let's go ahead and eliminate the y's. I'm going to multiply this top equation, say, by -1 here and rewrite it. So I have negative y equals negative 10x plus 20. And now when I go down the list here, I'm just going to eliminate the y's and I'm left with 0 on the left side. 3x minus 10x is negative 7x and then plus 77. And now I can move that x over and then I can solve. So it's possible to solve in this form, but now you're not one step away once you eliminate. And I could have saved steps probably just by doing the substitution method or graphing method as well. Plus, slope-intercept form doesn't always leave you with, integers. There are often a lot of fractions in the slopes there. Anyways, use that to solve for y. You keep going. But still, you can use it with larger numbers. I'm not going to solve this one by graphing. You already saw I wouldn't. Substitution and elimination, they panned out for me. They sure did. And the last one, it's simplest for solving a system with 3+ equations and variables. I did say this is for linear systems of equations. This is technically planar. I don't know if you guys know what planes are if you're in Algebra 1, but these are 3D objects here. It's straight, but it's a plane here. This is technically not quadratic or anything, so I think this might fit here. When you take an Algebra 2 based course, you're probably going to be solving systems of 3. I'm not going to do this here for you, but I'll let you know what. I most prefer elimination here. Now for me, that is in an objective standpoint. Subjective standpoint. It's not objective. Some people prefer substitution. But I'll tell you what, with systems of 3, oftentimes if substitution happens, it means you got to isolate a variable. Like I can isolate this z just fine by moving those guys over. But in any other variable here, I'm going to be left with fractions. And system of 3 is a lot longer than a system of 2. In fact, it involves getting to systems of 2 to then solve multiple systems of 2, plural. So it's just this weird go-to. But it's possible to do. I would solve using matrices personally, so that's another step. Okay, so that's elimination pros there. I'm going to jump to the elimination cons because there are cons. I want you to see the examples, and this is when I would avoid elimination. This is when I would not do it. So let's look at it as a big nutshell here. Not very useful. Sometimes it does this. Not speaking for all students, but blah, blah, blah. All right, what do these all say? Let's get started. Not very useful when equations are not written in standard form, of when a variable is already isolated, or an equation that contains fractions. I'm not going to do a fraction one with you here, but let's see one that's not in standard form as it stands. This is really calling for substitution. I think you have to agree. I could also graph it, but this is really calling for substitution. It really begs for me to just go ahead and put it in there. I know it's a little cumbersome with the distribution and all that, but it's ready for you. By the time that you move it over for elimination, you're doing just as many, if not more, steps. And you'll probably avoid mistakes doing it through substitution right now in a problem like this. Just distribute and move on. If I want to solve using elimination, I need to move the x's on the same side of the equation by subtracting that 3x over. And now I probably got to rewrite that top one. And then I got to do some equation manipulation to go ahead and, get the... probably eliminate the y's, right? So I'm working through a couple things. Not impossible, not terrible, but not very useful. Substitution is the most useful in that problem right there. Although fractions are mitigated, and we talked about that, fractions are mitigated here. Sometimes it requires multiplying both equations into a larger least common multiple, making much larger numbers. What I mean by that is, if you're going to try and solve using elimination here, we got to line these things up so they are additive inverses. Well, do you know what the least common multiple is of the numbers 10 and 14 are? It's 70. And you'd have to know that. You might think it's 140, but it's 70. And if you don't know it, you're going all the way up to 140. I'd have to multiply these by 5. I'd have to multiply these by 7. And, this is already going to get massive on me already. These are going to get huge for me to eliminate the x's. In fact, I have to multiply one of these by a negative probably, just to make one of them a positive 70x, one a negative 70x. These numbers are going to get huge. Okay, well, what about the y's? Well, what's the least common multiple of these two numbers? 42. So I'd have to multiply this one by 6 and this one by 7. So the numbers in this, and obviously this is an extreme example, but it's a real one. It's a legit one. Probably -7 again. But it's a legit example here. These numbers are going to get massive on you. And look, the fractions would be mitigated that way. This particular problem, I would look at that closely and I would tell myself, maybe it is better to go ahead and do substitution here. Even though, look, the numbers will still stay big unless you kind of can play with other parts here. And look, this has to do with elimination too. I could divide all these by 2 to help me out as well. You know, there are other ways around this, and I didn't talk about this with the substitution thing to begin with, but I could divide those there. I could divide these by 7. I don't know if you noticed that. I could divide these numbers by 7 and get -2x minus y equals 6. You know, but that's something that you wouldn't look to do through elimination normally. It's kind of like the thing I said with the substitution in parallel lines and stuff. If you're looking to substitute immediately, you might not put something in slope-intercept form that you normally would to know that the lines are parallel before you start. Same with elimination. If you're playing so much on multiplication, you might forget the fact that some things are divisible by numbers because that's what you would do when you're isolating in substitution to get a y by itself or something. So anyway, obviously this makes it a lot easier for elimination now. But when it comes to substitution as well, I could isolate that y pretty easily, have myself no fractions, and be good. Not trying to steer you away from elimination on that, but I myself might seek alternative methods. Honestly, this would be my first go-to, dividing. You'd have to know about it though. Okay, because this method is best approached with both equations in standard form, once one variable is solved for, there are still several more steps in solving the other variable, as it is not isolated. So, you know, just right here, again, I'm not going to get far into playing with telling you all the little nooks and crannies in this thing, but let's say you got an x equals 5. Okay, now you got to solve for y. I got to plug it into one of these two equations. Either this one, 9 times 5, or -4 times 5, and solve for y. And then you got a couple more steps to do. All right. So unlike the substitution method where you already have a y equals equation ready to go and to plug that 5 in, here you gotta, after multiplying this, you gotta move it over, and then you gotta do the division. Again, not the biggest hassle in the world. I'm done. But and look, I'm not saying these are, I don't know if these are the answers or not. I have no idea. But for this one right here, you know, if I just plug it in right there, I'm just doing my computation then and there, alleviating myself from any mistakes. Look, I just made a mistake. Did you see this? That was unintentional. I just made a mistake. Alleviating myself from any mistakes as I'm going about it that way. And, you know, not to pick and choose which formula, which one has less negatives, instead of just go to the isolated one, it's then and there and ready. Okay. 3 more bullet points and then I'm all done. Unless applied in real-life context, this is the same thing that I said for the substitution one. I think I can move on from this one. Same exact. These are the same examples too. I'm not going to play with elimination, but the same idea. I have no idea what these things are really telling me, except for this is where they intersect. I guess that means they're parallel, but I don't know how far away I could. But you know, the graphs really do help for that kind of context, or for that kind of not context, but that kind of visualization. Okay. All right. I'm not speaking for all students when I say this, but students can be forgetful in doing a couple things here. Now, when I say I'm not speaking for all students, I'll be speaking for enough of my students that even after I warn them, this still happens. What is it that I'm talking about? Reversing signs when multiplying by a negative, and also forget to multiply the constant. Let's say you wanted to eliminate these x's. That makes sense because there are already 2 x's lined up. Maybe you multiply this by 2 to eliminate y, but let's say you wanted to eliminate the x's. Okay, I'll multiply this equation here by -1, and we'll get, you know, let's say I'm one of those students. Okay, -2x, boom. Okay, minus 2y equals the -1 times the -14. There we go. And then I go and eliminate, and I get 2y equals all this stuff. I've made a mistake. And I don't know if you know what it was. If you multiply by a negative here, notice how this sign didn't change. That happens a lot. It happens a lot, especially when it's not the first term you looked at, or when that -1's not right next to it. Notice how I reminded myself to multiply the -1 by the 14 because it was right next to it. People don't always write it there, and they might forget. that negative, sometimes people just say, oh, minus, here's a negative. Oh, okay, just keep it as a minus. No, it's got to turn into a plus. This has got to be a plus. This turns into a 6. The whole equation changes. Look, I'm not calculating these things correctly. I said negative 28. It's negative 24. Clearly, I'm all over the place with that. But just keep that idea in mind that can be a lost portion. That doesn't get forgotten as much in substitution, except for distributing a negative, which is kind of this. But people get forgetful there a lot. And then they're like, oh, hey, Mr. Robinson, what happened in the problem? Well, there's your problem. You know what I mean? What's the other one? Forgetting to multiply the right side by your chosen value. So let's say on this one I wanted to eliminate x over here. I'd probably multiply the top equation by 3. So say, okay, times 3. So, okay, so that's 6x minus 18y. And I don't know what it is, but I'll tell you what. Maybe because this number gets too big and you're looking at the equals. This happens all the time. Equals negative 26. I didn't multiply it by 3. Uh-oh. And that's a big problem. This happens a lot. A lot. Okay? Don't be the one to let it happen to you. Be consciously aware of distributing that 3 everywhere. Maybe it's because the 3 is far away from it. Maybe because you're so busy saying the number equals and making sure you go, oh shoot, which one was it? Was it this number or this number? Which equation was I looking at? It happens a lot. You got to multiply by that 3 and make that, what is it, negative 78. So right there, okay? A lot. Not speaking for all students, but it does happen. And finally, not often a viable method to solve past linear systems. If I did this quadratic one right here, using the elimination method, probably use substitution at that stage, elimination really stops being very beneficial once you're using linear systems, once you're not using linear systems. All right, so that's going to do it for this one right here. What I'm going to do is have a follow-up video where I'm going to have 12 problems. I'm going to have a checkbox list of solved by graphing, substitution, or elimination. I'll let you know which ones I'm going to do and why I think those ones are decent, and if I and then I'll solve using those methods. But I want that to be faster. This was a 50-minute video here. So I'm going to cut this one short, or I'm going to cut this one off right now. If you want to go to that next video and look at those 12 practice problems that I do, again, they'll be scattered linear equations. That I'm going to be solving using different methods there, but I'm only going to use them if they're decent ones to use for that set. Okay, so that'll do it for me. I'm Mr. Robinson, signing off. Catch you later.